Today we're going to talk about a SIP, communication protocol request. We're going to see how we do, what are the different transport layers that we have. Some are known and some are less known. We're going to see how we do it in Arnacon and a little bit of cryptographic 101. So a SIP request. A SIP request stands for Session Initiation Protocol. It's a request that have many fields inside it, that each of them has a specific responsibility in order to establish, modify, or terminate voice or multimedia sessions with a server or with other recipients. A secret request, as we can see here in the picture, is an example that we see a register on the top left. The type of the request is written. We have many request types, like registration. We do options, a register. We have an invite, acknowledge, cancel, to update. We have information. When we want to send message, we have a specific one. Each of these specific requests have their own sets of values that can be sent inside a request. So if we go back to the request, we can see, for example, that we have via. Via stands for from where the request initialized from. We can see here the transport type, that's a UDP type. We can see here the IP, the port from that IP address, the branch. This is a unique identifier that the server can know to return to after the request. We have max forwards, that's the amount of different servers or clients that can hop on the way until the request is arriving to its destination. It's a default value, and if it increases more than that, the request is terminating. We have a to and a from where to who. We have a call ID, that's a unique identifier to know that this is a request. We have a CSEC that is allowed to the server to know which order of the request the requests are arriving to, so we can track and then handle by the correct order. We have expire, and we allow from which responses we are allowed to this request, and we have some user agent and more. A SIP request is basically a JSON that is full of parameters that we're sending, and then the server with a specific tool knows how to parse it into and handle it. We have the different requests here. We can see here that on the server side, we have the request route on the left side. This is when a new request is arriving to the SIP server. It starts and handles everything from top to bottom. And then we can see here for like a couple of examples, we see that one is an invite, one is a cancel, and one is acknowledge. And then we know how to handle correctly by the request type. Like we've seen before, we saw that the request before was a UDP type. We have 3 or 4 main requests of transport layers that can be used in order to handle the communication. We hear about them a lot, we use them a lot, and this is what they mean more in depth and the actual settings and qualities of each of it. So we can see here that UDP, it's traditional VoIP telephony gateways, is very lightweight. TCP, it's little less lightweight. It's really reliable, and it's stateful. It means that it can hold the current state of the communication that we have. A TLS, it's an encrypted TCP, and we have a WebSocket for it. In TCP, we also introduced something called NAT. NAT, it's a way for different devices on a private network to go into the public network and be able to know from which of these devices on the private network we initiated the request from. So for example, we have 4 different devices and they operate on the same Wi-Fi with different ports. Then the NAT will keep mapping between the private IP and to the public IP that we are getting out in order to reach the response on the other side. More in depth, we have UDP. It's a user datagram protocol. It's very lightweight. It's common for very lightweight applications that doesn't need to use any stateful, so to keep the current communication between the of the session. It's like a mailman that is carrying a letter and is putting it inside the box. We know that the letter arrived, but we can never know if someone tampered it on the way. It's prone to attacks, and no one can reply to it directly. It needs to send another letter, so it's stateless. Then we have TCP. TCP is Transmission Control Protocol. It establishes a three-way handshake between the clients and the server. It's sending the request and initiates a key that all these three knows about, and then they can communicate safely between those two. It's order, it's no errors, it's continuous byte stream, so we can trust that the packets that arrived in this communication protocol is arriving on the same order, not like a mailbox. This is, it simulates like a phone call. Whenever someone answers our phone call, we can trust that the order in the call is arriving. It's not like I'm gonna say something and then the end of the sentence is gonna be broadcast first and then the beginning. So it's stateful. It's keeping the current state of the communication between us. We can see a comparison here between UDP and TCP, that's stateless against stateful. It's a three-way handshake. It's reliable. The order is guaranteed. NAT is much easier in TCP. In UDP, it's not because of how it's being built. Speed is very fast in UDP, and it's used for lightweight desktop communication tools. And the overhead as well is very low on UDP against TCP because it's stateless in UDP. TLS is a transport layer security. It uses asymmetric encryption for handshake with symmetric encryption for the data transfer. This means that the two clients that talk with each other, they are exchanging keys between them, and the server and the clients as well. And then and then a man in the middle or tampering is non-existing in TLS, because we are sending a request that we want to initiate a session, and then the server or the client is responding with "this is my key" encrypted with the public and the private key. It ensures cryptographic integrity and authentication, which TCP doesn't. We can see it whenever we encrypt a request on a SIP server with TLS. We can't see it arriving into the server. We have to decode it with the server private key before we can see the data. Comparison between TCP and TLS, that TCP is the public way of sending things, and TLS is the private things of things. It's encrypted, it's with nonce checking, it's verifying the identities in the end, and it detects any changes or tampering on the way. How we do it in Arnacon? In Arnacon, we're also sending SIP requests, but a little bit different. We are still relying on the transport layers to be as it is, but we are heading to the traditional SIP request, some custom parameters. We have an XData and an XSign. A question: from which client did the SIP register here arrived?
0x4e.
From which client device? We can't see, basically. We see it also from a local IP. We can't really see. If we recall the previous request, where in the beginning, we saw a user agent, Zoiper, and then it knew that it arrived from here. On this request, I simulated a SIP request only from Manos, from an AI that sent a JSON with these parameters to that server, and it managed to parse it. In Arnacon, we use XData and XSign, and the from can be a plain Ethereum address or an ENS. An XData, it's a UUID4 concatenated with a timestamp in milliseconds. That's the old way, and we upgraded the system in order to support the new EIP 712. with structured and typed data. We see here that it's declaring the which data it is before with some custom parameters. And then afterwards, we are filling these parameters with actual values. So in this specific way, we took the name, version, chain ID, and identity and timestamp, and then gave it the actual parameters that we're using in order to authenticate a request letter. The X sign, it's a ECDSA with an EIP 191. We hear this ECDSA, SECP, TP, EIP 191. What does it mean? What is it doing? What does it mean to sign something? What is actual ECDSA? What it is? So an ECDSA, EIP 191, sorry, first. It's a prefix. It's just this prefix that we are adding into the data that we are signing in the beginning. And the ECDSA curve, it's a huge mathematical playground that is used for public key to derive the public key from the private key, that we have a signature components after we are signing something that we can get a V, R, and S values, and then from it we can recover who was the signer. Do you want to know how the signature components are being calculated with a little bit of cryptography? It's up to you.
Yes.
Yes. So SR and V values. SR and V values are values that are cryptographic calculated with the ECDSA curve that we see here. This is the functions that this is the function formula that we see here, while we see the Y and the X, and P, it's the finite field over this diagram. It's a little more discrete math here, so a lot of things will not make sense in the beginning, also for me, but the more we're getting into it, it will make a little bit more sense. We see that to calculate the R value, we do an R times X mod N, where R is a K, it's a scalar, that we can choose whatever scalar that we want. It can be 60 million, whatever. It's usually a very, very big scalar. It's the nouns. And then a G, it's a known point, fixed point that we use inside the curve. It's the X and the Y values are above. And then we are calculating the big R with it. And then in order to calculate the small r, that's the component in the signature that it stands for R, we're taking the Rx, the X value after calculating this, and then we're doing mod N, where N is a smallest positive integer over the finite field that the curve is initiated. It means that in discrete math, we have for every field a finite field in hexadecimal, for example, we have that the finite field is 16. So everything above 16 cannot be represented in the field way. So if we want to represent, let's say, 24, we don't have 24, so we take 24 and then we do 24 mod 16, and then we get 8, and then we can, inside this field, we can represent the data. So N is the 16 in this case. And again, because we have the fixed G, we can calculate it with this N. It's also a very, very big prime number. So in order to guess this K with an actual mathematical computer afterwards, it cannot do it. This is why it's considered safe, because no computer can calculate this amount of times in order to reach this K back, because the possibilities of a prime combinations are endless. And then in order to calculate the S in the signature components, we do the K inverse. The inverse number inside a finite field, it stands for the opposite number of a number in order to receive 0. So K times K in the power of -1 equals 1. Let's say in the finite field of 16, we say if 5, then we complete it into 9. 11, sorry. H, it's the prefixed message with the EIP 191 hash with KESAC 256. That's a mathematical formula in order to receive it. The R we found on the before. D stands for the private key that we have. We all have private key that is 32 bytes. We can take it and put it here. And then all of this, we're doing mod n because we are still in the smallest positive integer that is inside the finite field. Then we're getting the S. V can be whatever we want, 27 or 28. Most chains calculated with chain ID times 2 plus 35, 36. And they hiding for you how they choose it in the signed transaction. And usually they are putting something in the signed data in order to tell the recover where it comes from in JavaScript, Python, or some of the other. This is the new era of communication. We are happy to be a part of it.